Matter on Earth can exist in any of three states: gas, liquid, or solid, and can change from one state to another. In this section, you will examine these changes of state and the factors that cause them. First main idea: substances in equilibrium change back and forth between states at equal speeds. Some liquid chemical substances, such as rubbing alcohol, have an odor that is very easily detected. This is because some molecules at the upper surface of the liquid have enough energy to overcome the attraction of neighboring molecules, leave the liquid phase, and evaporate. A phase is any part of a system that has a uniform composition and properties. In a closed bottle of rubbing alcohol, gas molecules under the cap strike the liquid surface and re-enter the liquid phase through condensation. Condensation is a process by which a gas changes to a liquid. A gas in contact with its liquid or solid phase is often called a vapor.
Equilibrium is a condition of balance. Changes in temperature, pressure, or concentration can cause a shift in the equilibrium. When an ice cube is dropped into a glass of water, the ice warms and melts. At the same time, the rest of the water becomes cooled until the overall temperature stabilizes. Reversible chemical reactions also come to equilibrium. When aspirin combines with water, such as when you initially swallow a tablet, some of the aspirin forms ions. The stomach's acidity, however, provides high concentrations of hydronium ions, one of the products, pushing the equilibrium back toward the reactants. Another reversible reaction occurs when nitrogen dioxide, a pale yellowish-brown gas, converts to dinitrogen tetroxide, which is colorless. A decrease in volume causes an immediate increase in pressure. The reversible chemical reaction responds to this change, pushing the reaction toward product. Since the product is colorless, the overall color of the gas appears to lighten. Le Chatelier's principle states that if a change is made to a system at chemical equilibrium, the equilibrium will shift to oppose the change until a new equilibrium is reached. In this case, more N2O4 forms to relieve the stress of increasing the pressure. The product side of the equation results in fewer overall particles than the reactants.
If the temperature of the liquid remains constant and the cap remains closed, the rate at which molecules move from the liquid to vapor remains constant. Near the beginning of the evaporation process, very few molecules are in the gas phase, so the rate of condensation is very low. As more liquid evaporates, the increasing number of gas molecules causes the rate of condensation to increase until the rate of condensation equals the rate of evaporation, and a state of equilibrium is established. Equilibrium is a dynamic condition in which two opposing changes occur at equal rates in a closed system. Even though molecules are constantly moving between liquid and gas phases, there is no net change in the amount of the substance in either phase. Equilibrium, vapor pressure of a liquid. Vapor molecules in equilibrium with a liquid in a closed system exert a pressure proportional to the concentration of molecules in the vapor phase. The pressure exerted by a vapor in equilibrium with its corresponding liquid at a given temperature is called the equilibrium vapor pressure of the liquid. The increase in equilibrium vapor pressure with increasing temperature can be explained in terms of the kinetic molecular theory for liquids and gaseous states. Increasing the temperature of a liquid increases the average kinetic energy of the liquid's molecules. This increases the number of molecules that have enough energy to escape from the liquid phase into the vapor phase. The resulting increased evaporation rate increases the number of molecules in the vapor phase, which in turn increases the equilibrium vapor pressure.
Consider a closed system containing a flask from which all the air has been evacuated. When liquid ethanol is added to the flask, ethanol molecules begin to leave the liquid surface to form vapor. Molecules continue to vaporize and condense until equilibrium is reached. A liquid boils when its vapor pressure equals the pressure of the atmosphere. In the evacuated flask, there were no molecules in the gas phase or atmosphere to exert pressure on the liquid, so the liquid boiled immediately. As more molecules from the ethanol entered the gas phase, they began to exert pressure on the liquid, slowing down this process until equilibrium was reached. The equilibrium vapor pressure of a liquid is the pressure exerted by the vapor in equilibrium with its corresponding liquid at a given temperature. Le Chatelier's principle states that a system in equilibrium that is subjected to a stress will react in a way that relieves the stress. Some of these stresses include changes in pressure, changes in concentration, and changes in temperature. Consider this reaction of nitrogen and hydrogen to form ammonia. A change in pressure affects only equilibrium systems in which gases are involved. If the pressure of a system is increased, the equilibrium will shift to favor the reaction that produces the fewest moles of gas. This action will reduce the total pressure of the system. In this example, more ammonia is produced to reduce the pressure on the system. A change in the concentration of one of the reagents also affects a system. If the concentration of one of the reagents is increased, the equilibrium will shift to favor the reaction that reduces the concentration of the added reagent. If more hydrogen is added to this flask, more ammonia will form to reduce the hydrogen concentration. A change in the temperature of a system can also stress a system. Reversible reactions are exothermic in one direction and endothermic in the other. According to Le Chatelier's principle, the addition of heat shifts the equilibrium so that the reaction that absorbs heat is favored. If heat is added to an endothermic reaction, the equilibrium shifts to favor the formation of the products. If heat is added to an exothermic reaction like this one, the equilibrium shifts to favor the formation of the reactants.
Every liquid has a specific equilibrium vapor pressure at a given temperature. The stronger these attractive forces are, the smaller is the percentage of liquid particles that can evaporate at any given temperature. A lower percentage of evaporation results in a low equilibrium vapor pressure. Volatile liquids, which are liquids that evaporate readily, have relatively weak forces of attraction between the particles. Ether is a typical volatile liquid. Non-volatile liquids, such as molten ionic compounds, do not evaporate readily and have relatively strong attractive forces between their particles.
A volatile liquid evaporates readily. Consider what happens to the molecules when we put a volatile liquid in this flask. Some molecules leave the surface of the liquid and enter the vapor state. The vapor above the liquid exerts a pressure called vapor pressure in the flask. In contrast, a slightly volatile liquid has a lower evaporation rate, so fewer molecules enter the vapor state above the liquid. Non-volatile liquids have little discernible evaporation, so no vapor forms above the liquid.
Second main idea. A liquid boils when it has absorbed enough energy to evaporate. Equilibrium vapor pressures can be used to explain and define the concept of boiling, which is the conversion of a liquid to a vapor within the liquid as well as at its surface. If the temperature of a liquid is increased, the equilibrium vapor pressure also increases. The boiling point of a liquid is the temperature at which the equilibrium vapor pressure of a liquid equals the atmospheric pressure. The lower the atmospheric pressure is, the lower the boiling point is. At the boiling point, all of the energy absorbed is used to evaporate the liquid, and the temperature remains constant as long as the pressure does not change. If the pressure above the liquid being heated is increased, the temperature of the liquid will rise until the vapor pressure equals the new pressure, and the liquid boils once again. A pressure cooker is sealed so that the steam pressure builds over the surface of the boiling water inside. The boiling temperature of water increases, resulting in shorter cooking times. A device called a vacuum evaporator causes boiling at lower than normal temperatures. Vacuum evaporators, used to prepare evaporated and sweetened condensed milk, remove water from milk and the sugar solutions. Under reduced pressures, the water boils away at a temperature low enough to avoid scorching the milk or the sugar. At normal atmospheric pressure, which is 1 atm atmosphere, or 760 torr, T-O-R-R, or 101.3 kilopascals, kPas, water boils at exactly 100 degrees Celsius. This is the normal boiling point of water. The figure on the screen here shows that the normal boiling point of a liquid occurs when its equilibrium vapor pressure equals 760 torr. Energy must be added continuously in order to keep a liquid boiling. The temperature of a liquid and its vapor at the boiling point remains constant despite the continuous addition of energy. The added energy is used to overcome the attractive forces between molecules of the liquid during the liquid to gas change and is stored in the vapor as potential energy. Molar enthalpy of vaporization. The amount of energy as heat that is needed to vaporize 1 mole of a liquid at the liquid's boiling point at a constant pressure is called the liquid's molar enthalpy of vaporization, which is represented by delta, capital H, with a subscripted V. Molar enthalpy of vaporization measures the attraction between particles of the liquid. The stronger the attraction is, the more energy is required to overcome it, resulting in a higher molar enthalpy of vaporization. Each liquid has a characteristic molar enthalpy of vaporization. For example, liquid water's molar enthalpy of vaporization is very high due to its extensive hydrogen bonding. This makes water an effective cooling agent. When water evaporates, the escaping molecules carry away with them a great deal of energy in the form of heat. The figure on your screen here shows that the distribution of the kinetic energies of molecules in a liquid at 2 different temperatures. At higher temperatures, a greater portion of the surface molecules have the kinetic energy required to escape and become vapor. Third main idea. Freezing occurs when a substance loses enough energy to solidify. The physical change of a liquid to a solid is called freezing. Freezing involves a loss of energy in the form of heat by the liquid. In the case of a pure crystalline substance, this change occurs at a constant temperature. The normal freezing point is the temperature at which the solid and liquid are in equilibrium at 1 atmosphere of pressure, which again is also represented as 760 torr or 101.3 kilopascals of pressure. At the freezing point, particles of the liquid and the solid have the same average kinetic energy, and the energy lost during freezing is the potential energy that was present in the liquid. At the same time energy decreases, there is a significant increase in particle order, because the solid state of a substance is much more ordered than a liquid state, even at the same temperature. Melting, which is the reverse of freezing, also occurs at a constant temperature. As a solid melts, it continuously absorbs heat as energy, as represented by the equation at the bottom of your screen here. For pure crystalline solids, the melting point and freezing point are the same. At equilibrium, melting and freezing proceed at equal rates. The following general equilibrium equation can be used to represent these states. A solid plus energy is a reversible action with liquid. At normal atmospheric pressure, the temperature of a system containing ice and liquid will remain at 0 degrees Celsius, as long as both ice and water are present, no matter what the surrounding temperature may be. Adding energy in the form of heat to such a system shifts the equilibrium to the right. That shift increases the proportion of liquid water and decreases that of the ice. Only after all the ice has melted with the addition of energy increase the temperature of the system. Molar enthalpy of fusion. The amount of energy as heat required to melt 1 mole of a solid at the solid's melting point is the solid's molar enthalpy of fusion, represented with a delta, capital H, and a subscripted F. The energy absorbed increases the solid's potential energy as its particles are pulled apart, overcoming the attractive forces holding them together. At the same time, there is a significant decrease in particle order as the substance makes the transformation from solid to liquid. Similar to molar enthalpy of vaporization, the magnitude of molar enthalpy of fusion depends on the attraction between solid particles. Sublimation and deposition. At sufficiently low temperature and pressure conditions, a liquid cannot exist. Under such conditions, a solid substance exists in equilibrium with its vapor instead of its liquid, as represented by the following equation on your screen here. Solid plus energy is reversible with vapor. The change of state from a solid directly to a gas is known as sublimation. The reverse process is called deposition. The change of state directly from a gas to a solid. Among the common substances that sublime at ordinary temperatures are dry ice, which is solid CO2, and iodine. Ordinary ice sublimes slowly at temperatures lower than its melting point, which is 0 degrees Celsius. This explains why a thin layer of snow can eventually disappear, even if the temperature remains below 0 degrees Celsius. Sublimation occurs in frost-free freezers when the temperature of a freezer compartment is periodically raised to cause any ice that is formed to sublime. A blower then removes the water vapor that is formed. The formation of frost on a cold surface is a familiar example of deposition.
Some substances change directly from the solid phase to the gas phase. This process is called sublimation. When a substance undergoes sublimation, we say it sublimes. Dry ice, used to make fog at theatrical events and rock concerts, sublimes. It changes directly from solid form to a gas. Dry ice is actually solid carbon dioxide. Under normal conditions, the pressure is about 1 atmosphere. At 1 atmosphere pressure and room temperature, the phase diagram for carbon dioxide shows that solid carbon dioxide changes directly to gas. As the temperature decreases, carbon dioxide gas turns back into dry ice. This process is kind of like freezing, but freezing is the change from a liquid to a solid. The change from a gas to a solid is called deposition. When a substance undergoes deposition, we say it deposits. For example, carbon dioxide gas deposits to become dry ice.
Fourth main idea. Under certain conditions, water can exist in all three phases at the same time. A phase diagram is a graph of pressure versus temperature that shows the conditions under which the phases of a substance exist. A phase diagram also reveals the states of a system as they change with changing temperature or pressure. The phase diagram of water on your screen here depicts water existing over a range of temperatures and pressures. Note the three curves, AB, AC, and AD. Curve AB indicates the temperature and pressure conditions at which ice and water vapor can coexist at equilibrium. Curve AC indicates the temperature and pressure conditions at which liquid water and water vapor coexist at equilibrium. Similarly, curve AD indicates the temperature and pressure conditions at which ice and liquid water coexist at equilibrium. Because ice is less dense than liquid water, an increase in pressure lowers the melting point. Most substances have a positive slope for this particular curve. And point A represents the triple point of water. The triple point of the triple point of a substance indicates the temperature and pressure conditions at which the solid, liquid, and vapor of a substance can coexist at equilibrium. Point C on the phase diagram is the critical point of water. The critical point of a substance indicates the critical temperature and critical pressure. The critical temperature, represented by T sub C, is the temperature above which the substance cannot exist in the liquid state. The critical temperature of water is 373.99 degrees Celsius. Above this temperature, water cannot be liquefied, no matter how much pressure is applied. The critical pressure, P sub C, is the lowest pressure at which the substance can exist as a liquid at the critical temperature. The critical pressure of water is 217.75 atmospheres of pressure.
A phase diagram graphs the relation between three phases of matter. Pressure is plotted on the left axis, and temperature is plotted along the bottom. The body of the graph has regions that are either solid, liquid, or vapor. The temperature axis, the line from the lower left to the upper right, goes from low temperature to high temperature, so the solid region is on the left side of the graph. The pressure, on the left axis, goes from low to high, so the vapor phase is on the bottom of the graph. The liquid phase forms a V-shaped region in the top center of the graph. The triple point is where all three phases meet. This is the point at which there is equilibrium among the three phases, with solid freely converting to liquid and gas, gas converting freely to liquid and solid, and liquid converting freely to gas and solid. Another feature of a phase diagram is the critical point. The critical point is the end of the boundary between the gas and liquid phases. Above the critical point, the material is a supercritical fluid, which has some properties of gases and some properties of liquids. The critical pressure is found by drawing an arrow from the critical point to the pressure axis. The critical pressure is the lowest pressure at which the substance can exist as a liquid at the critical temperature. The critical temperature is found by drawing an arrow from the critical point down to the temperature axis. The critical temperature is the temperature above which the substance cannot exist in the liquid state.
Looking at the phase diagram of water again, we see that it indicates the normal boiling point and normal freezing point of water. It also shows how boiling point and freezing point change with pressure. As shown by the slope of curve AD, Ice melts at a higher temperature with decreasing pressure. Below the triple point, the temperature of sublimation decreases with decreasing pressure. Lastly, we see that, looking at the figure on the screen here, we can summarize the changes of state of solids, liquids, and gases. At this point, you should be able to explain the relationship between equilibrium and changes of state, interpret phase diagrams, explain what is meant by equilibrium vapor pressure, and describe the process of boiling, freezing, melting, and sublimation.